All right. Well, hopefully this time it does. I tried to record last class and then it quit on me, so kind of have to restart, and that's what's going to happen sometimes. But let's start with 44B, I guess. 44B. Um, again, if we had some bonds here, and I think we're going to talk about this again later on, but if we had these bonds here, we can talk about differences in polarity, which way the electrons get pulled, um, and putting partial positive, partial negatives on them as well. And if we had to organize them, I guess this would probably be the easiest one to start with here because that would be 0. They both have the same electronegativity. If we look at chlorine, it's 3.2. If I remember correctly, I think this is 2.2. Can somebody just double check phosphorus there? If it's wrong, just say something. This is 3.2 and this is 1. I forget. 9? I think. Is that right? Silicone? 1.9? Yeah? Okay. So again, this would be 0 here. This one here, the difference here in 2.2 and 3.2 would be 1, and then this would be 1.3. So we want to organize them in that way, increasing electronegativity difference, yes? Again, if we're putting partial negatives and partial positives, which is something you need to be able to do, we always put the partial negative on the more electronegative atom, aka the one with the higher number, okay, is the partial negative, partial positive. This one here, we probably wouldn't do that with because, of course, it's nonpolar, okay, and doesn't have, well, we're going to talk about that coming up here, okay, good? Questions, anyone? So be able to do that. Obviously, I gave you those 2 questions for a reason there, but you know that. 50. Let's talk a little bit about London. What are you going to tell me about London, somebody? Please, you tell me. If I have to describe London forces or talk about London forces or define what London forces are, where are you going to start? What are you going to tell me? Tell me something. Somebody, anyone. Before I start picking kids. Anyone. London forces. Start. The sooner you answer, the easier it is. Yeah, Luke. Yeah, nonpolar. Okay. When I write down nonpolar, what else am I going to put here with that? Nonpolar. What else can you say? What do you think? Anyone? Before I pick on Kaylin. Yeah. What else can I say? Anything? Anyone? Kaylin? Don't know. Sophie? What if I put this down? Temporary dipoles. Okay. Temporary dipoles. Why do I get temporary dipoles? What's that due to? Yeah, Luke. Exactly. So basically, the movement of electrons, yes? And at some point, we know that those electrons that go around and around are not going to be balanced out. And when that happens, when they're not balanced, when we get a distorted little bit, distortion or unequalness, I guess, or whatever, we are going to have temporary dipoles that are created. Yes? And of course, that affects, obviously, that's part of the size shape thing. We're not going to talk about that yet, but the more electrons you have, the more, the more chance of these temporary dipoles that you're going to have, right? So that's going to increase the forces. I would strongly encourage you to go back to the lesson 13 or so, 14, somewhere in there. and make sure you know the definition of these things that we're talking about, because I wrote this down, and that's okay, but this is pretty basic here. We need to understand what a London force is, all right? So I'm going to leave that to you guys because I don't want to give you just all the answers here, but you guys got to make sure that you know what a London, a dipole, what are you going to tell me about dipole? You know, what are some basic things that we need to know about dipole? What's the first thing you're going to tell me, Robbie? Yep, absolutely. Okay, that's probably where I'd start. Absolutely, polar. Second thing you're going to tell me is what? Somebody. Yeah, Aiden. Sorry, what? Yeah, absolutely. I like that too. I would definitely have something about permanent dipoles here. Um, okay. And why are they permanent? Here's the biggest thing. Those are all good places to start, absolutely. And the last one is that I'd probably add on to that a little bit is what? Somebody else? Anyone? Yes, Sophie. And why do we get that? Absolutely. Okay. So difference in electronegativities, and that's why we end up with that permanent negative end, permanent positive end, yes. Of course, they're partials, but they're not full positives. That's ionic. That's different. But we end up with those partially negative and partially positive ends. Okay? Definitely because of difference in electron. And even if we had a difference in electronegativity, that doesn't make sure we don't, that's not necessarily polar because they could cancel each other out, right? But we're just kind of talking about, well, it's a polar molecule. Somewhere in that polar molecule, there's going to be a difference in electronegativity, obviously, and therefore they would not like the forces aren't going to cancel out. And therefore, because of that, we have the difference in electronegativity, and that's what makes it polar, of course. Okay. And next, if we were talking about hydrogen bonding, okay, where could you start with that? We could say some of the same things, of course, because hydrogen bonding is nothing more than a special type of dipole. But what's a couple things you could tell me here? If I just said, hey, just tell me about hydrogen bonding, Kaylin. Stronger, yep. Stronger than regular dipole. Still not super strong, right? But stronger than dipole. Usually, not always. Yep, Kylie. Perfect. Okay, we need that H to bond it to N or F for that to happen anywhere in the molecule. It's fine. Okay, and then I would say those are great places to start. I would actually probably just, obviously we know this, but it's, again, got to be polar for sure. Hydrogen bonding's polar. Um, then this is where we have to get into the nitty gritty stuff here, and that's where it gets a little more complex. So you want to say things like, you know, even if we just had the simple example of HF, right, which is hydrogen bonding, yeah, we have the negative end, yeah, we have the positive end. But don't forget, here is the bare positive nucleus, right? Or nearly bare anyway, if not bare positive nucleus. Because remember, these electrons right here are probably spending more time over here, yes, kind of thing, especially with HF. It's super, super polar. So we're probably getting this, and again, we're left with, instead of this just partial positive end, we're left with basically one proton in the nucleus, yes? So we get a proton in the nucleus. Over here on this end, we get the very negative end because we have partial negative. So that's part of it, partial negative. We have lone pairs on the electronegative atom, which, of course, in the notes, enhance the attractiveness. Okay, enhance the attractiveness. Very electronegative atom, so that's going to help pull that electron even closer to it. So again, we have this kind of set up to it, roughly. Very positive end right here. Very negative end right here. And then, of course, we're going to have another molecule, don't forget. We have to have another HF in order to have, what color can I use here? This hydrogen bonding between these two here, yes? The very, very positive end to the very, very negative end. I wouldn't draw probably a line there, but I don't know how else to do that without, kind of showing that. So we have that very, very negative end attracted to the very, very positive end, okay? And don't forget, it has to be between molecules, of course. Okay, good. Anyone? Again, I would encourage you, I mean, that's kind of the rough idea, but again, I'd encourage you to go back to your notes. Oh, good. Go back to your notes and look through those. Okay. All right. Where are we now? Intermolecular. Just simply make sure you know it's between molecules, right? Between. That's really all we need to put there, I guess, for the most part. And intra is what holds one together, one molecule together. We've done that before. All right. Let's move on here. 55. I think is next, unless I told you something else. Don't forget drawing Lewis diagrams, otherwise known as electron dot diagram, same thing. So we're just going to do valence electrons. Make sure only valence electrons. We don't want any protons or neutrons here getting in our way, because we want to just have a representation of what that's going to look like. Yes. So neon is a noble gas. We'd want to have 8 electrons around it, even though there's, I know it's quite far down there, but well, maybe it's not actually. I guess it's not, but we want 8 electrons around neon. Beryllium, I guess, would look a little something like this here. 2 electrons, I think. Something like that. Phosphorus is 5. 1, 2, 3, 4, 5 valence electrons. Okay. Iodine would be 7, even though, again, it looks like there's way more, but we only go up to 7. It's in group 17, which we know as the halogens. And what's the last one? Lithium, I guess. Lithium's got 1. Okay. So those are what we should have for that. Good. Okay. We're going to do some drawings here, I guess, and we'll talk about a little bit of this. There's probably 1 or 2 here, I guess, in the next 2 questions here. I'm going to probably skip them because I don't think we need to worry about them. So my bad for giving you those. I thought they were good, and then I went to go draw them yesterday, and we didn't really do any like that. So we're just going to, unfortunately, skip them, I guess, or fortunately, whatever. The first one here is we need to draw Lewis structures for each of the following molecules. If it says draw Lewis structure, that just basically means do a drawing of this. All right. So we have OCF2, which I think I usually write it as COF2, but whatever. You'll remember this one. This is a pretty common one that we've done before here. We've had them on a few quizzes. Looks a little something like that. And then I probably put an F here, connect those two, connect that. And then I'd probably put an F here, something like that. And then, of course, we have this electron, we can make a double bond there. So all said and done, probably your best drawing. Remember, we want to get these electrons as far apart as possible. Something like this here. Okay, and we would know that as AX3, of course, trigonoplanar, which we're going to do on the next section here. This would be 121, 121, 118. Definitely polar. Probably dipole in this case. All right. Good. Questions, anyone? Put your hand up if you got any questions or whatever, and if I don't see you right away, I will eventually here. So, all right. Next. What do we got? Oh, H2, NH2. So again, probably start with the ends in the middle, right? Because they have the best bonding capacity. H's are kind of like the add-on, right? So we don't have to worry about those. I'm going to put an H there, connect them, and I'll put an H here and connect them. Again, we can add up, we got to connect these, of course. And it looks like we have 2 left over here. If I, let's see, and actually, yeah, I got to put an H here and an H here. Yeah. So we get some kind of look. That's good enough for that one there. Okay. Something like that there. HCN, I'm going to do this one somewhat quickly here. We've done this one a few times. This is this molecule here, yes? AX2 linear, 180 polar, dipole, because remember, H is bonded to the C, H is not bonded to the N here. So that's just dipole. This is definitely hydrogen bonding here, by the way, right? Quite a bit of hydrogen bonding. Okay, good. Questions, anyone? Okay. What's next? Cl2O. Again, you'll recognize this one. It's kind of got this. Probably start with O here. Cl. Okay. So AX2E2 tetrahedral bent. 104.5 polar, most certainly, and of course dipole again there. Okay. The one we're going to skip is probably E. If you really want me to draw that, I probably can, but I think we're going to skip that one if that's okay. If you want me to draw it, I can, but it's up to you. We definitely need to be able to draw NO3 or need a little practice with, of course, some polyatomic ions because it's been a while, right? So probably 5 here. We're going to add up electrons, don't forget, for these ones. So don't forget to add up the electrons. That's 24 electrons. All right. Okay. 24. Now, we're going to draw a skeleton structure. So step 1, add up electrons, draw a skeleton structure. Make sure you connect the outside atoms to the inside. 1, 2, 3, 4, 5, 6. We are going to complete the octet for the outside ones. So that was what, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And then again, we're going to have to move a pair in to make sure we have that octet for the central atom. So, whoopsies. Again, probably what we'd end up with, I'll make the double bond in over here this time, whatever. And then we want to get electrons away from each other and electrons away from each other. And don't forget this part, because that's the brackets we need there to make sure we have a polyatomic ion and, of course, a -1 charge. Okay, and if we don't put that there, then the question becomes, where do we get the electron from, right? So otherwise, we're just drawing NO3, and that's a little different. All right. Yeah. Okay. 58. Again, we're going to skip the first one, NO2. Let's just go to COCl2. I'm just going to go ahead and draw these if that's okay. If anybody wants me to add up electrons and do it with that instead, please ask. Put your hand up or something, and I can draw them with count. You know, again, we don't have to match these up perfectly. We can always count up electrons, and if you want me to do that, just let me know. I can do that. Most of these match up pretty nicely, but of course, sometimes they don't, and if they don't, we add up electrons. So we'd have this. This is AX3, trigonal planar. This is the 121, 121, and 118. Polar, dipole. Okay, all those things would go with that. Okay, I don't think you need everything of that, but nonetheless, that's what you're looking at for that one there. Okay. See backside here. We've drawn most of these already because there's only so many options we have for these drawings, right? In this case here, NOF, I would probably start with N in the middle. Okay, this does kind of matter a little bit because we do want to make sure we have the right central atom. If we don't, we could draw it wrong, so that's important. O here, connect, right? I'll put the F here, connect, and we have this one and this one left, so we probably should connect those two and make a double bond there. This best drawing, of course, when we get to VSEPR, the whole idea of VSEPR is, don't forget, valence shell electron pair repulsion. We want to make sure that the electron pairs are repulsed from each other. That doesn't make sense, but we want to make sure they're repelled from each other and the repulsion is maximized, okay? And that's why we have this drawing here. We're trying to get this lone pair away from there, that from there, and these spread out as well, okay? The bond angle on this one, by the way, was 120. If you remember, this is called trigonal planar bent. And of course, it's polar dipole dipole. All right. Good. Let's go to the next one here. Questions. If you got questions, just yell out something. CH3Cl. Again, you can put the Cl wherever, or the HV wherever you want. That's AX4 tetrahedral. That's 104.5 polar, right? Etc. Okay, probably dipole dipole in that case. PCl3 would look a little something like this here. Oops. Okay, PCl3, that's trigonal pyramidal. Don't forget AX3E trigonal pyramidal. H2S2. Again, we want to make sure that we have these in the middle. And H's, of course, we can slap on anytime. I'll put one there. I'll put one there. And we'll do that there. Okay. Something like that there would be a good drawing. All right. Now, for the shape for this is something that usually I might ask you, but you have to just kind of remember which is the central atom here. So this is a possibility. Obviously, it'll say, you know, what is the shape around the S or the carbon or the nitrogen or the whatever. So if I wanted to do the shape around the S, remember, this is my central atom is what they're saying. That's the A. This is an X. That's my central. That's an X. Remember, I don't care about anything else. Bonded to an X, bonded to an X, bonded to an atom. E, or sorry, E and then E, yes? So this is probably AX2, E2 in this case, AX2, E, okay? So that's tetrahedral bent, of course. I'm not going to make the Wookiee noise today because that's weird. R2D2, C3PO, Chewbacca. Ryder wants me to do it. That's baby Chewbacca. Actually, you can't see what I'm doing right now. Well, maybe you can. I don't know, but I could probably get like a recording, and it'd be awesome. All right, and that was N2H2. So again, let's get a crazy color here. N2H2. So probably something like this. I only need two H's. Remember, there's an electron here and electron here. And we connect those two probably. So probably the best drawing would be something along this line here. And we probably want to put these down here like so. Okay. As far as the shape here, I guess, you know, if you had to pick a shape, I don't like this one as much, but A, this would be X, this would be X, and then we have the E there. So that's probably AX2E. That'd be that trigonal planar bent one again for that. Okay. Any questions, anyone? All right. Sure. All right. And almost done here. 60, I forget now, just polarity. CH2, oh, actually, I think in the other class, by the way, I did 59. I know I don't think I gave you that one. You definitely want to know which molecules are polar and non-polar. So if I give you a list of polar and non-polar molecules and I say which ones are polar, which ones are non-polar, remember, if you're not sure, don't chance it, draw it out, right? If you're in doubt, draw it out. That rhymes. I think that's the second time I use that now. But make sure you draw it out. So if we went back to those I guess, which I'm not going to be able to do because I don't know how this thing works apparently. If I can go back here to this one, I guess, obviously, again, rules for nonpolar are simple. AX2, AX3, AX4, all the X's have to be the same. This is AX3, so this has got a chance, but of course, the X's aren't the same, so this automatically becomes polar now. So polar, well, that's definitely polar, 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 because it's got E, polar, it's got E. So it looks like to me like a lot of them are polar there. Most of them are polar, okay? So, but again, if I give you a list of, I don't know, say 8 compounds or 5 compounds, and we have to pick out the polar ones, make sure you're able to do that, okay? Or non-polar ones, whatever. CH2Cl2, just a little reminder here. There's a couple ways you can draw this. What do you have to remember about these? Obviously, this is AX4, yes. Tetrahedral. What do you have to remember about these tetrahedral ones? Anyone? AX4, tetrahedral. What do you got to remember? Is this polar or non-polar? Polar. Looks like it's non-polar though, right? I mean, it looks like those forces could cancel out, but why don't they? Somebody. Three-dimensional, right? So these are three-dimensional. So we, of course, don't have these across from each other like we've drawn them, yes? So maybe even a better diagram would be something like, it doesn't matter, but obviously if we had a, maybe this would be a little bit better here, where we can kind of tell a little bit easier which ones, or in this case, they don't cancel each other out, right? If you had to go through and put electronegativities on here, or slash, let's say I talk about, hey, tell me something about this C to H bond here. Is this a polar bond or a non-polar molecule? Which one is the partial negative? Which one's the partial positive? That's something you need to be able to do for Thursday, okay? Again, if you're not sure, look up some electronegativities. That's 2.2, that's 2.6. This would be the partial negative, that would be the partial positive. Yes, same thing here, partial positive, partial negative right here. When we get to this part of the molecule here, I think this is 3.2, so that's partial negative here. And again, this would be the partial negative here as well, okay? So when you draw it like this, it makes it a little bit more clear what end is the positive, what end is the negative. These ends here would be the negative ends. This would be the positive ends here, okay? I mean, you can do the same thing with this molecule. That's fine. It's just a little harder to show that, but it's going to definitely have, it's definitely polar. It's going to have a negative end and a positive end, okay? Good. Questions, anyone? Again, if you just want to focus on one part of the bond or one bond there, then like I said, that's what we're doing there, okay? And then lastly here, and then I just got one question, I'll leave you guys alone. C2H2, obviously start with the C's in the middle, right? This is 61, by the way. And then if we wanted to throw on some H's, we've got 2 H's to put on and 2 Cl's. Well, first of all, I'd probably want to connect these two for sure. So 2 H's and 2 Cl's. And I'll just kind of do this. And it looks like we got a double bond here too, don't we? Because we got those extra electrons there. So a couple ways you could probably draw this. Again, we do want to kind of get electrons away from each other, okay? So that's an okay drawing, nothing wrong with that. It basically says in 61, is this polar or non-polar? And in reality, this molecule be, and then the next section they say actually it could be both, okay? It could be polar, it could be non-polar as well. So just don't forget, I mean, we're not into this year, but next year we're going to talk about isomers, which are the same formula but different way of writing it. So there's lots of different ways to write this, or in this case, draw this. at this point here, you could ask yourself, is this polar or non-polar? And you could probably make a little bit of a case for both here, I guess, in this case. Mr. Berg pointed out, though, you know, what happens if I, for example, switch, you know, these two around here? What if I put the Cl here and the H here? Is that going to be non-polar or polar? Does that make a difference? That's probably got a better chance of being maybe non-polar-ish, perhaps, possibly. Or, you know, again, there's nothing to say. I know we talk about making things symmetrical, and usually we want to, but you don't know that the Cl is not here and the H's are here. Okay, that's a possibility too. I mean, it'd be different if they're different, like very different atoms, but we know that hydrogen only forms one bond and so does Cl. So maybe it looks like this. In this case, I almost guarantee you this is going to be polar because this is the negative end. That's going to be the positive end, right? Guaranteed. So that's definitely polar. But the other ones could be a little bit either. Again, in the big scheme of things, if we're talking about this molecule, or if I want you to compare this molecule, I don't think in the big scheme of things we need to worry about that too much. I think it'll be a slightly different question if we had to do that anyway. Okay, but that's one option there. Again, we might ask you, you know, let's talk about this C to H bond here. Which one's the negative? Which one's the positive? Right? Is that a polar bond or a non-polar bond? Et cetera, et cetera. And of course, that'd be polar. Difference in electronegativity. Higher the electronegativity, the partial negative end is that one. Okay? Good. Questions? One more question for you, and then we are done. Okay? We haven't practiced this for a little bit. Let's get you to draw out some. You guys go ahead and drew this for me. Drew this. Draw this, whatever. Magnesium fluoride. Go ahead and draw that for me right now. I'll give you a couple minutes.